Hey everybody, in this video I will do a code walkthrough of fine-tuning OPT 6.7b with QLoRA. And next I just need to import the model into the machine. So you pass your model ID and do the boilerplate code. All these lines are pretty standard, which is auto model for causal LM. And then you pass your model ID, and because I'm going to be using LoRA, so load in 8-bit is set to true. And the entire try catch block is just to handle a situation that for some reason the model does not load. And after I load both the model and the tokenizer, I'm just quickly doing a clear and cached memory to optimize GPU uses. And then I am going to prepare the model, and just three little things I'm going to do on the model. That is freeze all our layers, cast the layer norm in float 32 for stability of the training, and also cast the output of the last layer in float 32 for the same reason, that is for stability of training. Now, all these things are done mostly to optimize or reduce the VRAM usage of the current machine. So for this entire notebook, these particular three things are really the specialty of these small notebook and fine-tuning of the model, because the other parts of the codes are very much standard boilerplate kind of stuff that you will see in most fine-tuning with QLoRA and PEFT library. So let's understand these pre-processing parts on the model, and all of these three execution, this three execution plan is included or wrapped in this single util method, the prepare model for fine tuning. So let's just go step by step in this and understand what these are doing. So the first thing, param in model.parameters, param.requires grad equal to false. This is used to freeze the model parameters. In this context, freezing means these parameters will not be updated during the training process. This is particularly useful when fine-tuning a large model on a specific task where only a subset of parameters, like the adapters in this case, need to be trained. And then what I'm doing is casting layer norm to float 32. That is, which is the second point of this pre-processing. So to give a little background of these, that is casting layer norm to float 32. So quantization typically involves converting model parameters from higher precision format like float 32 to a lower precision format like int 8 or even int 4 sometime, to reduce model size and potentially speed up inference. However, certain parameters like those in layer normalization layers are sensitive to precision loss. So casting these parameters back to float 32 will help you to maintain numerical stability during training and inference, preventing issues like underflow or overflow. And hence the whole reason of doing this casting layer norm back to float 32, that is full precision. Now, I will come to this particular point, that is how this little if block is achieving this, that is casting the layer norm to float 32. But before that, let's quickly go ahead and look at the overall util method, and then I will come back to this detail. So model, here I'm enabling the checkpointing with gradient checkpointing enable method. So this reduces memory usage during training by storing only a subset of the intermediate activations. Instead of storing activations for every layer, it stores them for a few layers, and the others are recomputed during the backward pass. This is particularly useful for training large models on limited hardware resources. And that's exactly this line gradient checkpointing enable method is for. And the next line, that is enable input requires grad, which will enable the gradients for the input embeddings. This is useful for fine-tuning adapter weights while keeping the model weights fixed. And finally, casting output of the last layer to float 32, which is our point number 3 here. That is this one of the 3 points that we planned to do for preparing the model. So Similar to layer norm, the output of the last layer is cast to float32, and this is to ensure that the final output of the model, which is often used for calculating loss and hence gradients, is precise enough to maintain training stability, especially when the rest of the model operates in a lower precision format. And that particular job is being done with these two lines of code. And again, I will discuss this in detail, how exactly it's achieving that. Now, coming back to our previous point, that is how this little if block right here is casting the layer norm to float32. So the first I'm doing is dimensionality check, that is param.ndim equal to 1. This will check if the parameter dimension is 1. So in neural networks, especially in transformer, layer normalization parameters, that is scale and shift parameters, often referred to as gamma and beta, and these are one-dimensional. Each parameter in layer normalization is a vector corresponding to the number of features in the layer. But note that this approach of doing these kind of conditional check param.ndim equal to 1, this assumes that a uniform architecture where all one-dimensional parameters are from layer norm layers. While this principle is true for many transformer architecture, it's important to note that this might not hold for all neural network architectures. But in this case, we assume that this principle holds, and that's the reason we are doing this conditionality check. And so the most other parameters in transformer model, like weights of linear layers, are multidimensional. So according to this approach, this dimensionality check is a quick way to identify layer norm parameters. It's a heuristic that works well in practice because the 1D parameters in these models are typically from layer norm layers. And so when this condition is met, I am just converting the data type of these parameters to float32 with this line param.data.toTorch.float32. Now, a little bit more note on the layer normalization and this conditionality, that layer normalization is a technique used in neural networks, particularly in transformers, to stabilize the training process. It normalizes the input across the features for each data sample individually. Now, let's delve deeper into the specifics of layer normalization and the role of its parameters. So, unlike batch normalization, which normalizes across batch dimension, layer normalization works across the feature dimension. For each data point in a batch, layer normalization standardizes the input features based on the mean and standard deviation of those features for that specific data point. Now, layer normalization involves two key parameters. One is gamma, that is scale, and the two is beta, that is shift. Now, gamma parameter scales the normalized data. It is a learnable parameter of the same length as the number of features in the input. In essence, it multiplies each normalized feature to scale it. And the beta parameter shifts the scaled data. It is also a learnable parameter with the same dimension as gamma, and it adds to each scaled feature, allowing the model to shift the normalized values. And both gamma and beta are vectors, making them one-dimensional tensor in PyTorch. The length of these vectors corresponds to the number of features in the input to the layer normalization. For instance, if the input to the layer normalization has 512 features, both gamma and beta will be 1D, that is one-dimensional tensor of length 512. And the next concept is about identification in the model. So in the context of transformer models and many other neural network architecture, these are often the only parameters that are one-dimensional. Other parameters like weights and linear layers are typically multi-dimensional. For example, 2D, that is two-dimensional for weight matrices. And therefore, in a model checking these param.ndim double equal to 1 is a heuristic to identify these layer normalization parameters. it assumes that one-dimensional parameters in a model are likely to be either gamma or beta from layer normalization layers. Now, these parameters of a layer normalization are very sensitive to numerical precision. The operation in layer normalization, like standardization, which involves subtraction and division by the standard deviation, can be affected by the reduced precision in a quantized model. That is, in a model where a QLoRA or PEFT, things like these are applied to quantize a model to reduce its precision. And hence, casting these parameters, that is alpha and beta, to a higher precision like float 32 helps in maintaining the numerical stability of these operations, ensuring that the normalization process does not introduce significant errors. And the next thing I want to discuss about this code is that how does this block cast the output of the last layer into float 32 for the same reason, that is for numerical stability of the training. So this class cast output to float is a subclass of nn.sequential, and its main purpose here is to override the forward method. So the cast output to float class wraps a LM head, that is language model head of the model. This ensures that the output of LM head is cast to float 32. Now let's examine how this is achieved. So class cast output to flow creates a new class that inherits from PyTorch's nn.sequential. The nn.sequential is a container module that sequentially applies the modules it contains. And inside this class, the forward method is overridden. The forward method defines how the module processes input data. In this case, it calls super.forward to apply all the operations of the original LM head module on the input X. And after processing the input through the original LM head, the output is cast to float 32 with this same method, that is to torch float 32. And this ensures that regardless of the input data type or the internal processing of LM head, the final output is always in float 32. This is crucial for maintaining numerical stability, especially when the rest of the model might be in a lower precision format due to quantization. And this last line here, that is model.lm head equal to this class. So this replaces the original LM head of the model with the new cast output to flow wrapper. This means every time the LM head is used in the forward pass of the model, it will be through this new wrapper, ensuring that the output is always in float 32. Now, the question you might ask is why the code here is only casting the output of the LM head of the model. So the LM head is a linear layer that takes a transformer's output and projects it back onto the vocabulary space to generate the output tokens. And the LM head in a large language model, which typically refers to the final layer responsible for producing the actual token prediction. For example, a linear layer in a transformer-based model is crucial for the accuracy of the model's outputs. This layer often deals with large vocabularies and requires high precision in its computation to maintain the fidelity of the prediction. In mixed precision training, where most of the model operates in lower precision like float 16 or float 8 to gain computational efficiency, certain parts of the model might still need higher precision to avoid issues like underflow or overflow and to preserve numerical stability. The LM head, being directly responsible for the final output, is a common candidate for such treatment. Now, the gradients of the loss with respect to the outputs of LM head are particularly sensitive to precision. Inaccuracies in these gradients can significantly affect the quality of the model. A model update. By ensuring the LM head operates in float 32, we reduce the risk of precision-related issues impacting the learning process. And the rest of the model might not require such high precision because the intermediate representations within a transformer model are often less sensitive to small numerical errors. Thus, they can benefit actually from the efficiency of a lower precision quantized model. And lastly, this approach balances computational efficiency with numerical stability. While float 32 operations are more computationally expensive than float 16, applying float 32 only to the critical parts of the model like LM head allows for overall faster computation while still maintaining the model's performance integrity. Alright, so that pretty much explains every part of this util method, and I discussed this in so much detail is because this is pretty much the crux of the story of this notebook, because other parts of this notebook is rather very simple and very easy and very boilerplate kind of code. And anyway, so moving on, I then have a little util method print trainable parameters. So this function iterates through all the parameters of a given model and calculates two matrices, which is the number of trainable parameters and the total number of parameters in the model. So when I'm iterating through all the parameters, that is with this line for underscore param in model.named parameters. So this function retrieves a generator of tuples where each tuple contains a name and the parameter tensor for each parameter in the model. The underscore in this loop discards the name as it's not used in this function. And then for every parameter, param.numel is called. This function returns the total number of elements in the parameter tensor, effectively calculating the size of the parameter. This is added to all param to accumulate the total number of parameters in the model. And then I'm checking this little thing, param.requires grad. So this check determines whether a parameter is trainable. In PyTorch, parameters with requires grad set to true are considered trainable, meaning gradients will be computed for these parameters during backpropagation. If a parameter is trainable, its size is added to trainable params. Finally, the function prints three pieces of information, that is the total number of trainable params, the total number of parameters in the model, and the percentage of parameters that are trainable, calculated with this formula. And this is just this util method will just for representing the kind of efficiency gains that I'm doing by bringing in quantized QLoRA and PEFT into the model training. And next here, I'm defining all the LoRA config. So these parameters are very standard parameters, and you can read more about them in Hugging Face. But anyway, I'll give a quick introduction of them. And once the LoRA config is set up, create a PEFT model with this method get PEFT model function. It takes a base model, which you can load from the transformer library. In this case, this is our model, and the LoRA config containing the parameters for how to configure a model for training with LoRA. So this getPEFT model method is designed to facilitate efficient adaptation of pre-trained models to specific tasks or datasets while minimizing the number of parameters that are needed to be updated during the training process. So in the context of large language models such as those based on transformer architecture, fine-tuning typically involves updating a substantial portion of the model's parameters. However, PEFT approaches aim to fine-tune only a small fraction of these parameters, thereby reducing computational overhead and memory requirements. And this getPEFT model function essentially creates a modified version of the original pre-trained model. It introduces parameter-efficient components like adapters, low-rank matrices, or prompt tuning tokens. These components are designed to be trained while keeping the majority of the pre-trained model's parameters frozen. This approach retains the general knowledge captured during pre-training, while the trainable components adapt the model to the specific task at hand. And with that, all the pre-training jobs are all done actually, and now the final training. So you defined your dataset. Here I'm using English quotes, this dataset, and then you do this little data arrangement or data processing, data.map, and you pass a lambda function. And here I'm just applying the tokenizer on this quote column. So if you just go into this data, you will see the dataset structure here. And then you define your trainer, which is coming from transformers.trainer class. And here are all the standard parameters you define, your model, training data set, which is coming from this data, and only the train portion. And then you pass and define all your arguments for the actual training. So per device, train batch, gradient accumulation steps, warm-up steps. These are all very standard, and there are detailed documentation in Hugging Face, and generally you can search a lot of them in Google. So I'm not talking more about them. All right. Now here I'm doing model.config.useCache equal to false, and this will silence a warning. But for inference, you may think of re-enabling them. And these two little lines, if you want to push it to Hugging Face Hub. Otherwise, right now I'm not pushing, so let's just or let it be like this. And then model push to hub, you pass your username and the name that you want to give to your quantized model. Because here I'm using LoRA, so it's just OPT 6.7b LoRA. And here you of course need to it will ask you, the notebook will ask you the API token from Hugging Face, and you need to just paste it. And that's it. Your model is already pushed to, your trained model is pushed to Hugging Face in this way. And then you can pull in that same model that you just fine-tuned or trained right now with these lines here. So here I'm again defining my PEFT model, that is my quantized model that I just trained, and defining my config, and then the standard things. I'm bringing in the model, I'm defining the tokenizer, and using PEFT model to properly convert that model. And finally, the inference. And for the inference, I have this little util method, generate text, where it takes input text, and the model, the tokenizer, and a default parameter, max new token. So you just define your batch by applying the tokenizer on your input text. And then with this line, with torch.qda.map.autocast, I'm setting a context manager and then getting my output tokens by invoking model.generate on the batch and also specifying the max new tokens. Now, a quick word on these context managers. So with torch.qda.map.amp.autocast, this statement in PyTorch is a context manager that enables automatic mixed precision, or AMP, for the enclosed block of code. So AMP is a technique used in deep learning to improve computational speed and reduce memory usage while maintaining the model's accuracy. So when autocast is active, certain operations in the code block are performed in a lower precision than the default, and the primary precision used in autocast is float 16, also known as half precision. This lower precision allows for faster computation and reduced memory usage in compatible hardware, especially for NVIDIA GPUs that support tensor cores. And also note, autocast is designed to be a seamless optimization. It automatically selects operations that are safe to perform in lower precision while keeping others in full precision. This balance is crucial because some operations like reductions or certain activations can suffer from reduced accuracy or numerical instability in lower precision. So in this code right here, the autocast context is applied to the model.generate function call, ensuring that the inference computation for large language model is executed with mixed precision. This results in a more efficient utilization of the GPU, leading to faster inference times without a significant loss in output quality. Alright, that was a little code walkthrough video for this fine-tuning of opt-BNB large language model. And stay tuned because I'm going to do many such videos over the coming weeks. Thank you very much for watching. See you in the next one.